Hello friends, this is going to be a video about the basics of dealing with sequences. I am still getting used to recording videos, so forgive me if some things don't quite turn out right on this one. Well, as far as equipment is going, I am making use of an iPad with an Apple Pencil. If that is a piece of equipment you happen to have, it may actually make some things convenient later on. So in any case, what we're going to talk about then, as I said, was sequences. Let me see if I can get the share screen to work right now. And that will take just a second here. And then I tell it mirroring Zoom. All right, you should now be able to see what is on my iPad screen. Yay. All right, so the notion that I want to communicate here is that our idea of sequences is somewhat similar to things that you have dealt with before. Everybody's used to the good old XY plane, and ideas like the X coordinate and the Y coordinate. And if I had a point there that I would call 1, 2, it means that I go over 1 unit in the X direction and 2 units in the Y direction. If it's negative, I go down instead of up, or left instead of right. So if we do things in 3 dimensions, and we will be getting there fairly soon this semester, then we have to think about an X, a Y, and a Z axis there. On a side note, you will probably deal with Don Smith, and he is an evil physicist, and they reverse where the X and Y axes are. Not a big deal though. If we again think about an X coordinate of 1 and a Y coordinate of 2, we'd have a point here maybe of being 1, 2, 0, but we could go up 3 units from that and have something that would be 1, 2, 3. Okay. And so it should be pretty obvious that you can continue that on and talk about something that goes 1, 2, 3, 4. And if you just continue it on forever, you can have 1, 2, 3, 4, ... that continues forever, but that we think about as being a single thing. Now, we can't draw those. We just can't draw things that are infinite dimensional. But that kind of intuition about comparing them to something we can draw is kind of nice, right? And it's also inconvenient to make infinite lists. So we also need another sort of way to look at these. So the next thing we will think about is a comparison to something else you dealt with. You have in the past dealt with functions like f of x equals, and I'm just making up something real quick here, x squared minus x, and then you thought about that as a graph on a plane. Well, when we talk about sequences, the change in notation is going to be that we tend to use an N or a K or an I or something, but we tend not to use an X for it. And so if I just change this here and said N squared minus N, that would be really the same function that you're used to dealing with. It's just that the input for that function, you're no longer going to be putting in things that are not integers for it. Okay, so if we wanted to talk about this sequence we were talking about up here, we would say a sub n is equal to n, and that would then in one fell swoop, specify for us the each and every one of those infinite number of coordinates. So then there's something a little bit abstract there in that you could assign anything that you wanted to any one of those infinite coordinates, but it may be really hard for you to think up a function that fits a particular thing that you happen to be looking at. So we're not going to worry about that too much. We are in general going to be thinking about sequences where we do have a function for it, okay? And so along those lines, I want to say something about a few just basic sorts of functions that you'll encounter pretty frequently. And it would be nice to put a name to them sometimes. So if we say something about an arithmetic sequence, this will be something that is a linear function. If you said your a sub n equals 2n plus 3, then you can plug in any n value for it. But remember that for sequences, we will generally be just plugging in positive integers. So you can say a sub 1 equals 5, a sub 2 is equal to, what's that, 7, a sub 3 is equal to 9. And the thing to note is, since the slope of your line was 2, in the sense of f of x equals 2x plus 3, then you're going to have an increase of 2 each time you increase the n value by 1. So that's the notion of these arithmetic sequences, is that they increase by a fixed value each time. Then you'll sometimes hear something that I actually am going to not talk about for the reason of trying not to confuse us. Okay, so let me instead say something about exponential. Now, you've dealt with exponential functions, of course, back in calculus and hopefully also in algebra. But if we had an exponential function, which I'll call e sub n, just e for exponential, that could be something like 2 to the n over 3. And then you'd see that e sub 1 is going to be equal to 2/3, and e sub 2 is going to be equal to 4/3, and e sub 3 is going to be equal to 8/3, and so on and so forth. The trick there is that your exponential functions, instead of adding 2 each time, are multiplying by 2 or whatever the base happens to be, okay? So with that kind of idea in mind, then let me say something about a recursively defined function. Because although writing the functions is super nice and makes things easy to deal with, that's not how you encounter them in day-to-day life. If you'd notice that a sub n that we had of, what was it, 2n plus 3, if you said that a sub 1 is equal, or sorry, a sub 2 is a sub 1 plus 2, and a sub 3 is a sub 2 plus 2, well, in fact, we could have just defined that whole thing by saying, I want a sub 1 to be 5, and for a sub n plus 1, each time you add 1 to the n, to be equal to a sub n plus 2. Okay? So you can have definitions like that, and similarly for the e sub n that we had there, 2 to the n over 3, you can spot that a sub, let me back up and say e sub 1 is going to be equal to 2/3. And then E sub n plus 1, each time you increase the n by 1, is going to be E sub n divided by 2 times the E sub n, because you're multiplying by 2 each time, right? Now we can have fancier sorts of things like something that you will hear referred to as the Fibonacci sequence. Okay, this is a recursively defined sequence that has something or another to do with reproduction cycles in rabbits. I'll try not to get into that, but the thing that we do on this one is to specify the first 2 terms as being 1, and then say that you take 2 consecutive terms and add them together in order to get the next one. So consequently, you'd have 1, 1, add those to get 2, add the last 2 there to get 3, and then 5, and then 8, and 13, and then 21, and so on and so forth. And in fact, what you will find out is that those grow super duper fast. They grow exponentially, actually. But the topic of how to go about getting the explicit function for that is a little bit beyond what we'll do. Note, though, that if you're looking to identify an arithmetic sequence or looking to identify an exponential sequence, you take consecutive terms and subtract, and if it's constant, then you've got an arithmetic sequence. If you divide and it's the same thing every time, then you've got an exponential sequence. There's lots of other sequences that you find by some trial and error stuff, but that's the essential bit that I want to say about the recursive definitions. Okay, then I want us to think a little bit about the idea of taking limits. And I'm not going to get into anything super technical. If you took limits in Calc 1, you can take limits in Calc 3. Well, this kind of limit, because all we're really doing is talking about limits at infinity. And hopefully, you've dealt with that sort of thing already. So let's go back here to the screen mirroring. And we will look at this one we had, a sub n that was equal to, what was that, 2n plus 3? Well, if I say limit as n goes to infinity of that 2n plus 3, as n goes to infinity, 2n is infinite as well. And when you add 3, it doesn't get smaller. So we actually get a limit of infinity there. When you talk about sequences, if you get a limit of infinity, you say that the limit diverges. Okay? And that will be useful for some things we do. However, you probably remember things like this as well. Okay, where we have 2 polynomials being divided, and we need to take the limit there for that. And that, if they have the same degree, you can look at easily and just say, oh, these 2 terms are going to dominate. Since they have the same degree, we can just divide the leading coefficients and get 1 out of that. If they weren't the same degree, then we'd have to do something a little bit different. Say, for instance, that I had this as my function. N squared, let's say plus 83, and over n cubed minus 3n squared plus n. Okay, just a quick example. Then when we took the limit as n goes to infinity there, we couldn't just divide leading coefficients because they don't have the same degree. So when that happens, the thing that you have to do is to identify the largest power that you're seeing. In this case, n cubed. Maybe a better way to say it is you identify the largest order of growth. That's a cubic. And then multiply the top and bottom by 1 over that. And when you go through and get some cancellation, you are going to end up with 1 over n plus 83 over n cubed on the top. On the bottom, you'll have 1 plus 3 over n plus, well, with the cancellation, 1 over n squared. Now, 1 over n to a positive power as n goes to infinity is always going to 0. And so that means we will have 0 plus 0 on top, 1 plus 0 plus 0 on the bottom. So we end up getting 0 out of this limit. Now, if you end up with 0 over 0, y'all know sometimes you got to pull out L'Hopital's rule on that. And that's fine to do on these because, you know, we need to be able to go back and use the things that we saw in Calc 1. So then one more quick example on this. And in this one, I'm going to go ahead and use some exponentials and have 2 to the n plus n squared divided by 3 to the n plus n. And if you're doing the limit on that one and applying that same idea, you know that exponentials grow faster than polynomials. So 2 to the n or 3 to the n is going to be what you have to divide by. 3 to the n, of course, is going to be growing faster than 2 to the n. So I'm going to take 1 over 3 to the n on both the top and the bottom. And now I'll be talking about limit as n goes to infinity. Can't draw my infinity symbol very well there. Of 2 to the n over 3 to the n plus n squared over 3 to the n divided by 1 plus n over 3 to the n. And you know that the 2 to the n over 3 to the n is really 2/3 to the n, and that's going to go to 0. The rest of it is a little bit trickier, but hopefully from L'Hopital's rule stuff, you remember that since polynomials grow slower, that when you do that division, you'll get a 0, and the same on this one. So we end up with a 0 on a limit there. Okay. So most of your limits that you're going to take with regard to this really just depend on remembering the Calc 1 stuff. We'll talk about factorials a little bit later, and factorials grow even faster than exponentials do. So lots of what we'll have happening is going to depend on remembering that a slow growth order divided by a fast growth order goes to 0. And so I think that should get us started on the basics of it. All right. Remember, if you've got questions, ask me. So, all right, thanks. And